now for the presentation, and I'll do that too. So Edwin, over to you.
Thank you so much. So good afternoon for those who are in Europe, or good morning for those who are across the ocean. I'm happy to open this session of our Health Data Interest Group, where the topic is achieving anonymity and correcting bias with synthetic data through generative artificial intelligence. In our discussion, we will deal with a series of issues relating to synthetic data. First, there's still controversial status as anonymous data, the deep learning methodologies currently used to generate synthetic data and synthetic imaging, their capacity to correct biased databases, the potential for augmenting specific patient cohorts and for creating virtual cohorts, their validation tests, their combined usage with other privacy-enhancing technologies. We know where the problem starts from. There is a challenge, a regulatory challenge with the health data sharing. The General Data Protection Regulation draws a dividing line between personal data and non-personal data. Anonymous data, that is, personal data rendered anonymous in such a manner that the data subject is not or no longer identifiable, according to the GDPR, fall outside of the scope of the regulation. Pseudonymization is the other method of protecting privacy introduced by the General Data Protection Regulation, indicating the processing of health data in ways by which they can no longer be attributed to a specific data subject without the use of additional information, provided that such additional information is kept separately and is subject to technical and organizational measures to ensure that data are not attributed to any identified or identifiable nature of person. So given their re-identifiability, pseudonymized data qualify as personal data and are subject to the GDPR. So this is a problem because anonymous data are very difficult to find, and differential and pseudonymous data are extremely cumbersome to handle. So whether health data can be considered anonymous or not is of paramount importance when coming to data sharing. Synthetic data have been attracting growing attention as a practical solution to the quandary of maintaining privacy in big data biomedical ecosystems. The issue of attaining anonymization through synthetic data generation in combination with differential privacy is key, as we will see. So the question is, can the creation of artificial data through differentially private generative adversarial networks allow scaling up experimentation with non-identifiable health data and effective training of clinical decision support tools? There are recent examples of usage of synthetic data. The UK government statistical service has defined synthetic data an unprecedented opportunity to innovate with data while safeguarding privacy and fostering public trust. Public Health England's National Cancer Registration and Analysis Service, which collects data on all cancers diagnosed in England, has been running a synthetic database called Simulacrum since November 2018. The United States National Institute of Standards and Technology has launched a differential privacy synthetic data challenge in 2019, showing a keen focus on developing a mathematical theory and set of computational techniques that provide a method of de-identifying data sets under the restriction of a quantifiable level of privacy loss. The difference between traditional anonymized data and synthetic data set is that these data sets protect privacy through the addition of statistically similar information rather than through the stripping away of unique identifiers, according to a review to an article by Belovin and others on the Stanford Technology Law Review in 2019. There are examples also by the latest working program for the European Union. The European Commission has announced some funding in year 2022 on two topics. The first one is scaling up multi-party computation data anonymization techniques, and synthetic data generation. The call refers to synthetic, i.e. artificially generated data, as they allow researchers and developers to test, verify, and fine-tune algorithms in large-scale data experimentations without re-identifiable personal data. The call's goals are to advance the state-of-the-art of de-identification techniques, to tackle the challenge of anonymized data sets that can be traced back to individuals, to develop innovative anonymization techniques demonstrating that effective data quality and usefulness can be preserved without compromising privacy, to explore and develop further the techniques of creating synthetic data, also dynamically on demand for specific use cases. If we go to the second project, the second call from the European Commission, again for 2022, this implies a sort of a potential acknowledgement of synthetic data within the operational workings of the European Medicinal Agency. The topic of the call is new methods for the effective use of real-world data and or synthetic data in regulatory decision-making and or in health technology assessment. Proposals are expected to produce robust evidence showcasing the value of real-world data and or synthetic data for healthcare regulatory decision-making and or for health technology assessment aimed at increasing the usability of this data in different use cases. Significant goals of this call are to test the ability of machine learning methods to help identify relevant real-world data and or synthetic data to match with and to interpret clinical trials, to assess and validate how machine learning methods can be systematically harnessed to screen a large amount of data, including unstructured data in many electronic databases, to identify factors affecting efficacy and safety of treatments and or digital health innovations for regulatory decision making and or health technology assessment. So these are important news which show the interest which is growing around synthetic data. If we look at how synthetic data are produced, we see that the methods to produce them vary, but the underlying principle is that values in the original data are algorithmically substituted with others representing statistically equivalent distributions and structures to create entirely new records with as little traceable relation to the originals as possible. Synthetic data are therefore fully artificial data which aim to achieve anonymity by breaking the link between private information and the data's information content. They usually are produced by making use of generative adversarial network scan called GANs, and I'll tell you more about this. And high quality synthetic data closely resemble the real data and to be a suitable substitute for processing and analysis. So what about these GANs, these generative adversarial networks, which have been one of the most important innovations in deep learning? GANs are based on two models playing recursively against each other. The generator learns to capture and recreate the data distribution. The discriminator estimates again and again whether the data created by the generator is fake or not. This allows, with important interpretability issues, to assess the overall statistical resemblance in the distribution and structure of the two sets of data. There is an important element which is differential private synthetic data. And GANs were working on this specific generation of differentially private synthetic data. Differential privacy provides an until now lacking mathematical foundation to privacy definition. Differential privacy works by introducing randomization into an analysis. The randomization obscures the contribution of any single record by ensuring that analysis results are essentially equally likely over any pair of databases that differ by the presence of a single record. Differential privacy serves to guarantee that the resulting data product does not carry more than epsilon bits of personal information from any record. This ensures that the data product is of marginal value for enriching inference attacks provided that epsilon remains small. There are two kinds of differential privacy, global and local. Global differential privacy is a technique employing randomization in the computation of aggregate statistics, and global differential privacy is meant to provide a mathematical guarantee against identity, attribute, participation, and relational inferences. Local differential privacy is a data randomization method that randomizes sensitive values, and local differential privacy is meant to provide a mathematical guarantee against attribute inference. There are important characteristics of synthetic data. They are used in the same way original data sets are, and therefore with the same storage, maintenance, and analytical infrastructures. They maintain statistical characteristics of the original data, but can be expanded for imputing missing data and augmenting real data. They can thus fill gaps, correct skewed value distributions, or remove spurious values in the original data, addressing collection, formatting, or normalization issues, which are pervasive in clinical data sets, and thus producing data that can even be more informative and realistic than the original ones. They can be produced at low cost for a variety of uses and in very large volumes to jumpstart AI development in areas where data are scarce or too expensive. So, can synthetic data really prevent inference attacks? This is a matter of hot debate. Some researchers have highlighted potential attribute disclosure risks, though globally validating synthetic data robustness in terms of identity protection. Protection from attribute inference can only be achieved if the generative model does not accurately reproduce all correlations found in the raw data. If the correlations that enable an inference attack on the raw data are preserved in the model's output, the gain of publishing the synthetic data in place of the raw data becomes however negligible. Other approaches state that attribute and inferential disclosure are both forms of statistical analysis, and therefore we would not want synthesis to protect against these. This appears in the latest book by Lemma, published in 2020, Practical Synthetic Data Generation. But there's a bunch of three brilliant young ladies who are researchers at the Polytechnic University of Lausanne and at the University College in London, who have spoken of a privacy mirage. They say that differentially private model training does not increase privacy gain with regard to linkage attacks. Any dimensions in the synthetic data that closely mimic raw data features increase the utility of the data, but simultaneously allow targeted differences about individual training records. The fact that it is impossible to predict the privacy gain of synthetic data publishing makes generative models relatively poor privacy mechanism, according to them. Synthetic data that perfectly mimic the raw data offer useful information for analysis, but simultaneously enable adversaries to infer sensitive attributes from partially known target records. If the synthetic data hide the patterns that enable the attack, they do so also from analysts. And so they come to the conclusion that synthetic data just offer a disparate protection. Protection from attribute inference can only be achieved if the model does not accurately reproduce all correlations found in the raw data. If the correlations are preserved, the privacy gain of publishing the synthetic data instead of the raw data is negligible. Differentially, private noise addition may hide some of the linear relationship that enable attribute inference attacks, but at the same time it reduces the utility of the data. While some records receive good protection from synthesization, others remain vulnerable to linkage attacks. It is not possible to predict a specific privacy gain. A high variance in the average privacy gain across target records indicates that the model tends to amplify the signal of some records in the training set, while it actually hides the others, finally providing only a varying and disparate protection. There are, however, possible ways of countering this. Making access to data contingent on specific agreements can strengthen protection. Authenticated access to data can be required. A variety of context controls can be enacted, such as access control, purpose-based access control, prohibition of linking data sources together, prohibition of re-identification, prohibition of data sharing, query monitoring and query termination, obligation to monitor additional information, obligation to comply with breach mitigation plans. So, well, these are all measures which can be taken, but which complicate the idea of having synthetic data as open data. There is one last point which has been hinted at by the call for next year by the European Commission, the first one. There is the possibility of looking for a combined usage of differential privacy synthetic data with secure multi-party computation. So we know that secure multi-party computation is a cryptographic modality aiming to create methods for parties to jointly compute a function over the inputs, keeping these inputs private. Secure multi-party computation allows a set of distrustful parties to perform the computations in a distributed manner, while each of them alone remains oblivious to the input data and to the intermediate results. The computation is considered secure if at the end no party knows anything except its own input and the result. There are current hurdles, and there is, however, a bright outlook for this. Privacy-preserving machine learning is an emerging field in data science. As yet, secure multi-party computation still implies a large communication and computation overhead, which makes it hard to use when very large amounts of data are required, since communication and computation costs are greatly affected by the increase of the number of the involved parties or of the model's complexity. But combining secure multi-party computation with differential privacy synthetic data is likely to be the solution which is needed according to the state of the debate as far as I've seen it to now. So this was a sort of a short introduction by me, and now I hand it over to Yanis, if he's there. Yanis, are you there?
Here, I'm trying to find my... Yes, I'm here.
Okay, good. So, well, the floor is yours.
Okay, can I share my screen, some slides I have, or share desktop? Okay, that's the entire desktop. Let's try how this will work. Your entire screen, application window. Give me a second to find.
You're done. Yeah, there you are. Good.
You see, it says, so do you see my first?
Yeah, we do see it. You must make it large.
Yes, let me do that now. Is it large now?
Not in my screen. It's still small.
Yes, it's large, but people, if they want to see it bigger, they have to expand the screen. But we see it perfectly.
But you see in presentation mode, not the slides to the left. Okay,
no,
great.
but we can expand it on clicking on the right, okay. And then it becomes full screen.
Maybe also if you don't have your camera on, Edwin, it may help. That's what I felt when you were talking. Anyway, so I will have a very brief introduction for precision medicine and privacy needs, and I mean, just for all of us to be on the same page, precision medicine is medicine that it follows that one size does not fit all. So it's medicine that is adaptive to special needs, special circumstances of each patient. So each one of us and each one of everyone in the world for the same thing may need special treatment. And that's because of the genetic profile, the same issue, depending on whether you have a gene or not, exposed or not, expressed, I mean, not exposed, expressed, then you may need different treatment. And also, based on the clinical observations may suggest a different treatment. And I want to say, why now? I mean, now meaning the past few years. Well, now precision medicine is picking up more and more because we have next generation sequencers, where we sequence, the entire genome as a whole and not just targeted ones. Tremendous advances in biomedical and genetic analysis. Bioinformatics has done tremendous work, but also wet analysis as well. And the pure informatics, big data, visual analytics, machine learning, very many advances. And given all this, let's not, the thing is, the emphasis that precision medicine is data-centered medicine. And I mentioned genomics that are collected, and based on the gene, you do various other things, including mutations, epigenetic modifications, and so on. But genomics bring transcriptomics with mRNA, and then proteomics, and then metabolomics. So all of this may affect the medicine that you want to apply to a particular person. And this is what precision medicine has done. So in Greece, a flagship initiative of the Greek government has been to create a national network of precision medicine on oncology, and that's the website of the network. And 10 research centers or university hospitals are participating to provide diagnostic and also analytical services on cancer to the public for free, subsidized by the government. And you see this is the logo. It's applicable to Greek nationals, so it's all Greek. But you see the 10 logos of the participants, and Athena Research Center, where Minos and myself we are affiliated with, next in addition to our universities, is this one. And together with one more, Democritus, we take care of the data side. So the idea is that you have 4 precision medicine units, and these are the medical oriented institutions that are participating with that. 2 in Athens, 1 in Crete, and 1 in Central Macedonia. And these 4 precision medicine units have, of course, geography helps. Where am I going to send my sample? But also specializations. And that is the flow of how things work out. So a doctor sends through an order system and asks for some analysis, genetic analysis, for blood cancers, solid cancers, hereditary cancers, and so on. The sample is sent for analysis through the system to the relevant precision medicine unit, where the next generation sequencing machine does its wonders, and we collect data here. And then the primary sequencing data, the first stage data, the reads are sent to the electronic infrastructure of precision medicine, where you have bioinformatics workflows to analyze targeting and so on and so forth. And you have a whole bunch of data here, including identifying particular mutations, because these are where they will lead you to a diagnosis and then a put simply treatment that is precise, personalized. And then because of this, with all the diagnostic data, they go to have a clinical report back to the doctor and so on and so forth, but also a diagnostic data analytics, where you keep all the cases. And here a clinical researcher or a medical researcher uses the entire history of this system, both for the diagnostic case reports to see what happened, but also the entire analysis of what others have done and what they have found. What are the main technological challenges? Complexity, not volume of data. The volume of data is not tremendous, but the complexity is tremendous, as generated by NGS. So in this side, this is complex. The second is advancing the analytical tools. Wonders have happened here. Lots more needs to be done. There is research going on in my medical field. And third, privacy and security. What does this refer to? Everywhere. You see red boxes and then data crossing the borders of these boxes. And these are private data of a patient. Okay, the doctor must know, but what about all the others? So every single gray arrow that you see has issues of privacy. And that's the broadest complexity. And if you see the website of the network, Some things could be that the cloud version is in the US, or the infrastructure, even in Greece, it's operated by Amazon, and maybe who knows where the machines are. Are they in Greece, are they in the EU, are they in China, and so on and so forth. So one of the biggest concerns that the network says is data protection challenges. And here is a consent form. It's in Greek. I didn't translate that. But this is that on the first page, the main thing, one of the primary things that it says is that patient privacy protection is key. So everything that goes, and let me go back here, synthetic data possibly could be generated by everything that is being collected until now. And work is done, and any advances in synthetic data has immediate application in how to handle the historical data that are created and pass it so that the researcher can do their job. And of course, other forms, SMPC, differential privacy, with or without, possibly synthetic data, although that will be truly, it requires some thinking on how to do the diagnosis itself. So both for diagnosis and for research and trend analysis and finding biomarkers and so on, the privacy is a big thing for the network of precision medicine that we have in Greece on oncology, and I'm sure it is everywhere. So whatever various elements, Edwin mentioned, Minos will discuss some of the efforts. Reality needs synthetic data, needs removing any biases, needs protecting the privacy. So everything that we do in this direction will have immediate application. That's it from me. Thank you very much. Let me stop sharing. Back to you, Edwin.
Minos, are you around?
Yes, I'm here. Okay.
So try and make your presentation visible.
Okay.
And then it's up to you. I switch off from the camera. Good, we can see it.
You can see it? Okay, good.
Yeah. Go ahead.
Okay, is it in presentation mode now? Oh, no, okay. Okay, good. So, again, thank you for inviting me here, Edwin. It's a pleasure to talk to you a little bit about some of the things we're doing on what I call differentially private data synthesis. So essentially, methods for producing synthetic data that give you differential privacy guarantees. And this is work that was initiated within My Health, My Data, but it's been going on strong, and we're actually working with other projects now, like the Human Brain Project, and also more recently, EU Can Image. I think that I'm not going to spend a lot of time on this slide. Why is it important to share data? I think both earlier talks actually made this very clear. So one of the key motivations here for us when we're starting out on this path was rare diseases. Rare diseases, as defined by the World Health Organization, are diseases that appear in less than 5 in 10,000 people. Mostly they have genetic causes, and about 400 million worldwide are affected by such diseases. Now, rare diseases raise a very significant statistical challenge in the sense that, you need to share data, right? There's just not enough data in a single entity, like a hospital or a country. So you need to share data across these federations of data silos, like hospitals. But of course, sharing data, as we all know, especially sensitive medical data, raises a lot of legal and ethical challenges. And of course, this doesn't just hold for patient data, but similar challenges also hold for genomics, neuroscience data, and any type of sort of medical data sharing, not just patient data, raises these types of concerns. Now, sharing data, and sort of private data sharing, right? Why is it so complex? I just want to make it a point that it's not as simple as we might think. So in the early 90s, people believed that, if I look at any record, I can very quickly identify what is known as PII, right? So personally identifiable information. And then if I just remove that PII from the record, then everything is anonymized and everything is fine, and I can share the data, right? So there was a very famous case of such data sharing, which is known as the Massachusetts Governor Bridge in the late 90s, where a hospital, a medical insurance company decided to share some of the data, and what they said was, that's fine. I'll just remove name and social security number, which are, which is obviously PII, and I can just then share the data, right? What can go wrong with that? Well, it turns out that everything can go wrong. Essentially, what happened was that, if you take that supposedly anonymous data set and you just link it with a publicly available data set, such as voter registration records, and you just take these two data sets, these two spheres here that I'm showing. So the green sphere is the supposedly anonymized data, and the red sphere is the voter registration records, and you just join them on three attributes: zip, birth date, and sex. It turns out that these three attributes are sufficient to uniquely identify about 87% of the U.S. population. Right, so essentially, by doing this join on these three attributes, these sort of quasi-identifiers, as they're called, I can then essentially link a name to the diagnosis, the sensitive diagnosis information, and then I can get information on the diagnosis of specific persons, right? And essentially, one of the people identified through this join was the then governor of Massachusetts, right? So that's why that's where the name came from. So essentially, what this shows is that PII is sort of a very difficult thing to identify when you're dealing with real data sets, and things that may not appear as PII, when you find the right information to link to, become very critical PII. Okay. Now, one approach that was used to try to mitigate this was various techniques that have been invented for combinatorial data anonymization, over which were a very intense topic of research in the late 2000s, in the early 2000s, right? So one of such methods that many of you may have heard of is k-anonymity. So what is k-anonymity? The basic idea here is you take a data set, and you basically coarsen some of the attributes and generalize some of the attributes to make sure that every entry becomes indistinguishable from other k-1 entries. So essentially, you have these buckets of k entries that look identical, and then given that you have if you have a large enough k, then you can basically essentially you cannot identify any single individual with a specific disease in this specific example, right? So here, on the left-hand side, you can see the original data set. On the right-hand side, you see a 4 anonymous version of the data set. So this was a very, as I said, a very intense topic for research, and people were dealing with various ways. So there's, as you can imagine, there's many ways you can produce a k-anonymous data set, and there was various techniques that were proposed for devising k-anonymous versions of data sets. But it turns out that this definition of privacy is also not sufficient. And let me just give you, give you a high-level picture of where the problem comes from. So let's take this very simple aggregate data set, where what we have is a table that discusses that basically shows the number of hospital discharges in New Jersey for ovarian cancer patients. Right, so this is so you have various characteristics of the population, and you have the age groups, and then for each cell, you just mention the number of such individuals, and you use a star to basically suppress counts that are less than 11. Right, so essentially, what you're achieving here is a form of k-anonymity where k equals 10. Okay. And so the argument here is I'm just releasing aggregate information, and these aggregates that I'm releasing are large enough so that I can claim that I have a 10 anonymous version of my data set, so everything seems fine. Well, it may be fine if you're releasing just one aggregate, but when you're releasing many of these aggregates, like in this table here, things are not fine again. So what is the problem? I think the problem is something you can very easily see. is that I can just very simply do some simple math on this table to get more information on things that I'm not supposed to learn. Right? So for instance, just by the fact that everything in column 1 adds up to 735 means that I can accurately see that for the age group 1 to 17, I have 3 discharges, right? So just doing some very simple inferences using this aggregate information, and this is just a very simple form of inference, but I can actually do more sophisticated inference attacks on this table, and I can actually get very tight bounds on specific entries in the table, right? So even though I'm not sure what the exact count is, I can very quickly tell you that it's between 0 and 2, for instance, right? So what is the problem that is shown here? That even if you have something that looks k-anonymous and you're just releasing aggregate information, the fact that you can see many of these aggregates allows you to infer things that you're not supposed to. And these are what is called inference attacks, right? By doing many queries and receiving supposedly private answers, I can synthesize something that I'm not supposed to learn. And again, from the specific table, it turns out that you can make very, very specific inferences, like the one that I'm showing you here. I'm not going to read it just to, but it basically shows you things like you can infer things about exactly one Native American woman diagnosed with a specific disease that went to this specific hospital in New Jersey and so on. So essentially, what we have seen in the past few years is, we've seen many examples where companies or organizations released supposedly anonymous versions of data sets, only to find out that they weren't really anonymous and that the anonymization was actually broken just a few months later. Okay, so one would dare to say that there may be no hope for data anonymization, and again, from sort of an intuitive perspective, this makes sense, right? Because if you're publishing data that has some utility, it has to somehow be correlated to the original data, right? Otherwise, there's no utility in the data. Well, if there's correlations, these correlations can actually be discovered and exploited through these inference attacks. And what's even worse, in recent years, it has been discovered that you don't even need to be extremely smart to figure out these correlations, right? Because you can just use a deep learning, deep learning AI to essentially put together very, very powerful inference attacks. No smarts required, okay? Essentially, what you do is you take an anonymization mechanism, which is typically public, right? So if I have an algorithm for producing k-anonymous data sets, that algorithm is typically public. So I can produce many, many examples of original data set and then the k-anonymous version of the data set. And then essentially, when I feed these examples to a deep learning algorithm, I can essentially figure out the correlations to the original data set, again, in a completely automated way, just using off-the-shelf deep learning tools, no smarts required. So I don't even need to be that smart to attack an anonymization scheme. And again, there's many examples of such powerful deep learning inference attacks in the literature. I'm just showing you one here, which was on an attack on a commercial image obfuscation system called P3, where essentially, you take the original image that you see over here, and you anonymize it by just removing some coefficients in the DCT, some DCT coefficients of the image. The publicly available image, if you look at it, it looks like a noise, right? So essentially, everybody, if you show that image to somebody, they're gonna say, yeah, it's anonymous, right? I can't see anything out of it. Well, it turns out that if you put this thing in a set of possible candidates, and you can use a deep learning classifier to very quickly pinpoint the right image, right? So if I use a deep learning tool, I can pretty much identify the original image from hundreds of others as the original image for this sort of gray image very quickly and very accurately. So essentially, this says, even though I'm not able to reconstruct the original image, I can with very high accuracy, tell it apart from other candidates, right? So in a sense, this breaks the anonymization scheme. Okay, so essentially, this says that maybe de-identification and data anonymization, is not exactly the right model, right? Maybe we need a better, more formal privacy model where we can actually reason about things in a mathematical way. And this is exactly what differentially privacy gives us, right? So this is essentially what we do with differential privacy. We provide a formal mathematical definition of privacy. This is, again, there's a lot of math here. I'm not going to go into the details, but basically the high-level idea here is this. Let's assume I have two different data sets, right? One data set where that carries my information, my personal information, and one data set that doesn't have it, right? So these are what we call adjacent data sets, and I will signify them by D and D prime. So D contains my information, D prime has everything but my information, okay? Now, we say that an algorithm is differentially private if when I run the algorithm on D and I run it on D prime, the output distribution is almost identical, okay? So essentially what this says is, if I take two adjacent data sets, one that has my information and one that does not, and I run this algorithm, then the distribution of outputs for that algorithm will be very, very, very close. Essentially, this says that, the effect that an individual record can have on the output of the algorithm is very, very small, okay? So essentially, by looking at the output, I'm not able to identify whether my information was in the data set, the specific data set that was used or not. And this is exactly the definition of differential privacy. Now, you can see here that there's this epsilon parameter here in the definition, which essentially calibrates, right, the amount of privacy versus the utility in the data set, and that's always like a big issue, how to set up this epsilon parameter, which is, again, one of these practical issues of how you set up a differentially private algorithm. But the nice thing about differential privacy is, as I said, it gives us a very formal foundation to reason about privacy. One thing you should note here is that differential privacy is a property of the algorithm and not a property of the data, right? So it doesn't really refer to the data set that was used for the algorithm. It refers to the algorithm itself. Now, the nice thing here is that you have these very nice mathematical properties, which I think would be desirable for any formal foundation that we would like to have for privacy. One such property is composability. So what this essentially says is that if I take a bunch of algorithms and each one of them is differentially private, and I compose them in some way, let's say I apply them in order, then the output of that composed algorithm, that composition of algorithms, is also going to be differentially private, and I can also quantify its guarantee. Okay, and there's many composition results that show you how you can compose differentially private algorithms. Another very interesting result is the post-processing lemma, which essentially says that if I take a result of an epsilon differentially private algorithm, so if I take an epsilon differentially private output, then no matter what I do with it, no matter what I link it with, no matter how hard I look at it, I cannot make it less differentially private. Okay? The only way I can make it less differentially private is by looking more at the data, right? So if all I have is the output of the algorithm, no matter what I do with it, if I don't look at the original data, it's not going to become less private, okay? And this is very important because basically it tells you that it eliminates linkages, right? So no matter what I link the output of the algorithm to, okay. Am I in presenter mode, or I'm seeing some comments here that I'm not in presenter mode? I'm not sure. Okay, let me see if I can try to get into presenter.
You were not in presenter mode, but we could see if you were all the same. Just go ahead, I think. But if you move to presenter mode, it will be larger.
Okay, let me try presenter mode. Okay, is this better?
Yes. Yes.
Okay, good. Okay, sorry about that. I wasn't looking at the chat. Sorry. So again, these formal properties like composability and like post-processing are really, really important. These are things that we would like to have to formally reason about any kind of privacy framework. Okay, and the post-processing in particular is really important because it eliminates these potential linkage attacks. Now, differential privacy is already deployed in the field. It's used by the U.S. Census Bureau to release population statistics. It's used by Google and Apple, so to collect information from cell phones. So it's really, I think, at this point, it's the closest thing we have to actually a formal mathematical notion of privacy. Okay, essentially, if we look at things like K-anonymity, L-diversity, all these mechanisms that I mentioned earlier, these combinatorial mechanisms, they can be seen as essentially ad hoc efforts, right? Here we have really a sort of a very nice mathematical foundation, and I think it's going to be very important to build on this because it gives us a nice way to reason about privacy as a concept. Now, the problem of generating synthetic data that is differentially private. One thing that Edwin mentioned, and I think I need to mention again here, is that synthetic data on its own, just saying that I've generated some synthetic data by building a model out of some real data set, and then I'm just taking stuff out of that model, and this is synthetic, so it carries no privacy risks. That's a very, very that's a wrong statement. Okay, essentially, especially if you look at the very powerful machine learning models that we're using today, things like GANs or VAEs, variational autoencoders. These are really, really powerful models, and they can essentially model the entire training set. So you can train a VAE to actually generate the full training set. Okay. So the data is synthetic, but of course, if you've replicated the original training set, then basically you've leaked out everything, right? So there needs to be some care when you're training these models, and this is where differentially private data synthesis comes in. Now, as we mentioned, differential privacy is a property of the algorithm, not the data. So how would we generate differentially private synthetic data? Well, the idea is simple. We will actually build a generative probabilistic model. But when we train it, we make sure that the model, the output of the training algorithm, is epsilon differentially private. Okay, so essentially during the training process, we will inject appropriate noise or appropriate uncertainty at certain stages in the training process to ensure that the output of that process will be differentially private. And once we have that differentially private probabilistic model, generative probabilistic model, essentially we can sample from it to generate a synthetic data set. And we can take as many samples as we want. We can generate a synthetic data set of any size. The nice thing here is that we can just cite the post-processing lemma that I showed you in the earlier slide, and just say that, since the model is differentially private, then whatever I take from it is also going to be differentially private. Okay, and then we can share that as an epsilon differentially private synthetic data set. Now, synthetic data sets, differentially private synthetic data sets is a concept that has been gaining a lot of steam. In the US, NIST held a differentially private synthetic data generation challenge. I think it was in late 2019, I think, and with a hefty prize, about $150,000, with many entrants, and they had some really interesting results. And similar contests have been popping up in different countries. So I think people are slowly getting used to differential privacy as the sort of de facto definition of privacy, and differential private synthetic data is the natural step to build data that can actually be shared using these mechanisms. Now, one thing that is really interesting in our setting is that we're looking at differentially private data synthesis at scale. Differential privacy traditionally assumes that data is centralized, but in our settings, data is often federated. So in many situations, you have data silos, for instance, across hospitals or across genetics labs. You cannot have you don't have the leisure of the luxury of actually putting all the data sets together in a centralized setting. So essentially, we need to figure out how to do this differentially private data synthesis in federated systems, right? And here's there's different options. So you can use variations of differential privacy, like local differential privacy, to do this. But you can also combine these things with tools like secure computation, which Edwin also mentioned. And it turns out that if you can achieve the right combination, you can actually get more utility out of your final data set. Okay, because local differential privacy, even though it works in federated settings, it can end up adding much more noise than necessary and actually decrease the utility. So we're exploring different data modeling tools in this setting. We've been working with Bayesian, differentially private Bayesian networks and differentially private GANs, and this is work that is still in process. One thing that is really important, again, is for us to figure out how to exactly combine differential privacy with secure computation. And just to very quickly give you, the pitch on secure computation. Secure computation actually refers to a setting where you have these federations of data silos, and these data silos are mutually distrustful, right? So they don't really trust each other with respect to sharing data. So they don't want to publish data or put data together in a centralized place. But at the same time, they want to run some analysis over the entire global data collection. And a tool like secure multi-party computation is a cryptographic tool that allows us to do these federated secure computations. It's essentially a distributed protocol where the raw data out of the hospitals is never actually published. What we do is we essentially put a lot of computations, push a lot of computations to the hospitals, and we're running an SMPC protocol among these hospitals. And in the end, all that is learned is the output. So essentially, we learn the output without really revealing any information to other parties. So just to summarize, differentially private data synthesis, I think, is going to give us a very nice formal foundation to have synthetic data with mathematical privacy guarantees. And I think the formal part here is really important in order to secure ourselves from things like potential linkage attacks and unforeseen types of attacks on anonymization schemes. In a federated data setting, particularly, it becomes very challenging. And I think this idea of effectively combining differential privacy with cryptographic tools like secure multi-party computation is going to gain even more importance in the years to come. I think there's a lot of potential for interesting, fruitful research here. And I think with differentially private data synthesis, I think we're slowly going to move towards practical, provably private data sharing. Differential privacy, as I said, is already used in the wild. And SMPC, even though initially it was thought of as more of a theoretical tool, and Edwin also mentioned that there's a lot of overhead involved with SMPC. We're slowly starting to see practical SMPC systems, and there's companies like Cybernetica and Partisia and Porticore that have actually built business models around SMPC platforms. So I think slowly SMPC is also going to gain more traction, and it's going to give us practical ways to do secure computation. And I think with all these developments, I think slowly we're going to move towards this goal of practical, probably private data sharing. And with that, I'll finish my presentation and give the floor to the next speaker. Thank you.
Thank you, Minos. So now I think it's Leslie's turn, and then we will start with the debate with those who are attending.
And actually, I think the way that I planned it is really to bring us into discussion at this point. So I planned a few slides and really have some questions for everyone, and then we'll see if my little polling thing works. But so far we've heard from Edwin really about synthetic data and some of the legal aspects to consider, some of the ethical aspects to consider. Giannis presented on the personalized medicine and the privacy needs as well. And then Minos talking about the methodology for differential privacy, and then of course, secure computation. So being the American in the group, I'll ask more of the philosophical questions. So that's the humor, just to let you guys know. That's about as good as it gets. So let me share. Okay, can you see this, I think?
Yes, we can.
Okay, so trust in synthetic data, I really just wanted to bring us into the discussion questions and then bring everybody back onto line. But let me go through them and then we'll come back to the questions. So one of the biggest questions right now is trust, and how do we trust synthetic data? And what we've brought up are things of trust and privacy. Some of the things we haven't heard as much as trust in the data itself, and then also trust in the decisions that are being made. So one of the things that I was thinking about is that, you know, there are bad actors, for instance, who can do inference attacks and re-identify the people that would be in the data that represent the data. But what about good actors doing bad things? So these are people that are legitimate researchers who take the synthetic data to use them to make assumptions with them, but don't necessarily understand the limitations of those assumptions and the validity of it. So I think we need to think through some of those things. While the main concern right now is privacy and what we need to think about privacy, we also need to think about the value of the data itself. Specifically, the example I like to use because I like to play games is when I was really into Angry Birds. There was a bug in Angry Birds that on level 3.3, you couldn't get to 3 stars if you were on an iPhone. And I was very upset by this. But the fact of the matter is, what's the consequences for me not being able to get to 3 stars? Really, it was me being frustrated. But what are the consequences for us making decisions upon data, whether they be real or synthetic? We just need to keep thinking about them in the synthetic context. What are the consequences for making decisions upon the data that really shouldn't be made? And I don't really have answers for these questions. I'm just posing questions right now to foster the conversation. So some of the discussion questions that we said we would talk about is we need to talk about the validation tests, the biases, the legal status of synthetic data, the deep learning methodology, some questions coming back to Minos's talk, the legal coming back to Edwin's, the deep learning methods, creating cohorts based off of these synthetic data, and then combined usage of multiple data sets and data repositories. So first, I want to pose a question, and that is, how do we validate synthetic data on real data if the synthetic data is statistically identical to the real data? Now, this question specifically comes from one of my students. Sorry, he's not a student. He is an intern with my company who is working with synthetic data. And we also talk about validation. So I'm posing this question to the group, then we'll get back to the discussion. But I want to see if this works. If you go to menti.com and enter this number or click on the link, let me go back and just give me a second. I put it in the chat. Then you should be able to answer this question. And hopefully I will be able to show you the answers. But it would be nice to have more audience participation about when you think it is responsible to use synthetic data. So give you a moment for that. And I'm hoping there will be other, for hypothesis generation. Okay, don't know enough to answer this question. That is definitely fair. And don't worry about spelling or typos. We do not care. When it is not responsible to use real data for teaching purposes without PHI disclosure to protect privacy, when there is not any individuals who might suffer problems, when you know exactly how it will be used so that you can make sure it is statistically identical. Lack of a real data, I think, is an interesting question. And research design and training, that gets back into teaching. For health data outcomes research, since synthetic data by definition should be enough for statistical research. These are really nice. I can say from my perspective, when I worked at Washington University School of Medicine, we ended up developing, this was before synthetic data became a thing, we ended up developing a synthetic data set that had a lot to do with Harry Potter, because what we found was that the students, when we were teaching them, needed some data to really understand how to work with the medical data, but didn't know how. So it was a great way to have a synthetic data set in order to just get their hands dirty on some data without ever having to worry about privacy issues. So I think this one is good. Thank you for your responses. And the next question we have is, how do we validate synthetic data? So we have this challenge that the synthetic data is built off of a real data set, but then there are known biases within real data sets. So what do you all suggest as the proper methodology to validate these for future use? So we have a few answers coming in. Excuse me. A couple of using similar but different data sets. Use a GAN that does this validation. Replicate patterns known in the real data. Concern about ability to find new patterns that are true. I think that'd be interesting to hear more about. Give it one more minute in case somebody's typing. Blind test against real data. Yeah, depends on the synthetic data. Validation of synthetic data could mean comparing the statistical outcome of a comparable analysis in real data. So I think what this is bringing up is that we need to think about how what is a valid way of validating synthetic data? Again, completely agree that it depends on what the synthetic data is used for. GANs comes up again, uses this principle to learn whether a synthetic data set is indistinguishable. Conceptually, the synthetic data should reflect the original data and should get validated against the original. Usually, though, in machine learning with that, we usually have a validation set that has been preserved in order to test against that hasn't been used in the training. And maybe there's a methodology in that. So really going to real world data. And I think there just there's a lot of work to move into this area. So thank you for participating in that. So those were some other questions. Again, we're going to come back to the discussion group, bring everybody on. How do synthetic data correct biased databases, but how do they perhaps add biases to the databases? Again, I'm just posing questions more for discussion rather than answering them right now. We already asked that. When is it responsible to use synthetic data? And then back to the discussion question, just as a reminder that we're looking at validation tests, biases, legal status of synthetic data, deep learning methods, when's it appropriate to use for creating cohorts and combined usage of multiple data. But not to leave you just yet. I want to remind those who did not get to attend International Data Week in Botswana that when we could see people and things, this is what we got to see. And the reason I always bring this up with trust is because if you ever go around monkeys, they're trust breakers. They are thieves. They will come and steal your croissant. And I think the point on this is, who do we trust, or the idea to bring up is who do we trust, and when is it appropriate to trust and when is it not? So that's just more of the humor. So I'm going to stop sharing and bring it back, and if all the presenters can come on. Then I think we can start. I'm just going to reiterate some of those questions, or you guys can start answering some that I already posed. And anyone in the audience who has questions, please put them in the there are some in Q&A. Okay, why don't we just start with those? What are your thoughts on the methodology in medical settings, on the differential privacy in medical settings, specifically in light of the warfarin study by Fredrickson? Is that Minos? I think that's probably to you.
Okay. Sorry, I can't see the question. Can you repeat it? I can't see it somehow.
What are your, if you go to,
okay.
Yep,
Q&A.
yep.
Okay, good. So the warfarin study and the warfarin paper, I think that there's a lot of discussion on even in the paper that Edwin mentioned on the synthetic data being served as serving as a privacy mirage and so on. So I think there's a lot of discussion on differential privacy and whether that is the right privacy definition. And I think given the warfarin study and the privacy mirage paper, what they say is essentially that even if you apply differential privacy during data generation and you get a differentially private synthetic data set, that still does not secure you from other types of attacks, like attribute disclosure attacks or de-identification attacks. And that is true, okay? And that was something that was done in both the warfarin paper and the privacy mirage paper. That basically they showed that if you have something that is differentially private and it satisfies the differential privacy guarantees, it still doesn't save you from disclosing the attributes of certain values, for instance, right? And that's in a sense reasonable. It's not something that's unexpected. It's something that that is just not covered by the definition of differential privacy. So what I want to say here is that there are still some open issues, and there's some questions as to whether differential privacy is actually the right definition of privacy or the, let's say, a complete definition of privacy in the medical setting, or whether we actually want to think about that definition with additional privacy and security. Safe locks, let's say, okay? Because certainly, the fact that it just gives us a nice mathematical model to reason should not be the only reason why we're doing this. It should also give us, some notion of privacy against attacks that we can foresee. So I think there's a lot of discussion. This is definitely open to discussion, and there's ways, and I think it's going to be really interesting to see how we can do this augmented privacy definitions, but at the same time, I think it would be important to not forego the formal foundation. I think the formal foundation of privacy really gives us a lot of leverage in giving guarantees, and I think that we need to think hard about differential privacy and how it can be perhaps extended to satisfy to be secure against other types of attacks. Okay. So I'm not sure if this answers the question, but I think the reference specific to warfarin, I think it's a very hotly debated topic, and I think some of the proponents of differential privacy have already responded to that paper, essentially saying that they've the paper is not really using the definition of differential privacy. It's sort of misunderstanding the definition. But I think there's a lot of work to be done here.
And so it looks like Simon put something in the chat to kind of clarify. Sorry, the main point of the question was more that in achieving differential privacy, the models based on the DP data was potentially harmful to patients. Is there something of a differential privacy bandwagon which leads to it being used badly? Or is it just, are those just kind of the way that you're going down to do checks right now?
Yeah, I mean, again, I think there's, yeah, it's been a while since I read the paper, but differential private data was potentially harmful to patients in the sense, I guess, that it was leading to wrong treatments. Yeah, so one thing I will say is that, you know, for my, the way that I view synthetic data, right, I would not say that synthetic data is something that you want to use for actually writing prescriptions to patients. Okay, I think synthetic data is a useful tool for doing aggregate analysis and learning things like statistical models and so on. But in the end, if it comes down to actually, you know, producing something that's sort of production quality and something that you put to test with real patients, I think one should think about more like tools like cryptographic tools like SMPC and these types of tools. To me, the synthetic data, the way I view this is more as a tool for data exploration. When you know you don't have access to data, you really want to explore the data and get some generic ideas and trends. I would definitely not say that somebody should be doing like personalized medicine or doing writing prescriptions based on results drawn from synthetic data. So, I mean, I would be cautious in using the data in these settings. Now, the specific, you know, the specific details of the warfarin paper, I will need to go back to. But again, my understanding, at least from the discussion I've seen, is that, you know, yeah, differential privacy is definitely not a panacea, right? I mean, we really need to think about how we use it, what type of noise we add, and how it affects the outcomes and you know, especially when we're referring to real patients. So yeah, I don't know. I think it's definitely an open issue. There's definitely sort of a DP bandwagon, as Simon also mentioned, but I think we need to embark on it very, very carefully. It's not a panacea for all types of privacy concerns, or you know, it's not by definition that it's going to give us something with high utility. You need to be very careful with these tools.
Thank you, Minas. I think that leads us into the next question quite nicely, which is in the chat, which is up a bit. But with synthetic data, how do you know whether you are posing a question that is that the synthetic data are valid for? And this is one that you know, I personally struggled with when I used, because the chances of people making decisions wrong decisions, right? So good actors, good researchers taking the conclusions that they find to make broader decisions than what it should apply for was quite a concern. But I think I'll turn to Edwin and Giannis, because maybe you have more practical experience with that these days on where things are, you know, how is that attached to the synthetic data? Are there, you know, labels that come with it when people use it? I don't know what the current practices are.
Well, I will try and say something which is a hope, but let's consider imaging. In imaging, you can have synthetic imaging, which allows to bring together things from a variety of places without concerns of otherwise falling into privacy problems and so on. So organizing a very large scale construction generation of imaging of synthetic imaging can allow using much more in-depth deep learning, machine learning systems for analyzing things. Now, how then the outcomes which come out of that are used in concrete treatment of patients? This is the responsibility of the clinician, but it can lead to have ideas to discover elements which otherwise he would have not looked at, and then he need to verify very carefully with the real data. I think that it is a matter of, well, we need to work on this the clinicians need to get accustomed to the fact that this is a potential tool which can help giving insights, but not directly responses to on how to work. But for the moment, we are struggling with the fact that big data, which are crucial for artificial intelligence, do not really work in medicine, because all the data are in silos, all the data are separated. Nobody can afford to get this. So the idea that with synthetic data based on differential privacy, we can get to something which becomes useful in this sense and allows big data to be there is very powerful. Now, we must be very cautious. We must be attentive to all the criticism which is coming around. I really welcome the latest the developments in the debate, because the fact that people start talking of privacy mirage or things like that, this shows that somebody has realized that this is a powerful thing. So is it really the response? Does it need still a lot of efforts more, perhaps in the direction of combining secure multi-party computation and the differentially private synthetic data? I don't know. This is probably the great challenge in front of us, but I think it's extremely stimulating, and it opens up a number of possibilities which are important.
Okay, if I can add something to that, I think the question also mentioned something about what synthetic data is used for, and whether it can be useful for certain things and not for others. And I think that's definitely a big debate. I think and it's been often seen in the literature that you generate a synthetic data set that actually turns out to work well for, let's say, building a regression model, but it doesn't work well for doing things like, say, random forests. And I think that's sort of natural, because when you define the model that you learn out of the real data set, you're sort of imposing some limitations on what the synthetic data can actually model, right? So I think in the end, the ideal situation for us would be to build these synthetic data sets in a sort of a purpose-specific way, right? So then how one would plan to use the data set, and you produce a synthetic data set with that in mind. So you could have sort of purpose-specific synthetic data sets that give you better utility, but then you could also think of a general purpose synthetic data set that just tries to capture some generic characteristics, but maybe is not as accurate as it could be when you're doing a specific learning task, right? So I think again, that's something to be seen, but I think that's sort of expected. If I know how the synthetic data, how one would plan to use the synthetic data, then I can possibly give them more utility for the same amount of privacy. And I think that makes perfect sense.
If I may add a very little thing, we talk about synthetic data sets. And I think in most people's minds, we have an image of a table with numbers in, or genomes and so on and so forth. But in medicine, there's a lot of information in text, the doctor's notes, and how synthetic doctor's notes from which then to analyze and so on and so forth, and whether it makes first sense to extract it and then come up with synthetic data of the structured things that you extracted, or first come up with synthetic reports and then extract it, and how do you deal with places and other elements that come in text, and what you can infer from text just by the context, although in addition to the the named entities and very particular things. I think it's a challenge that we'll have to maybe not solve, but approach anyway, in order to capture a big aspect of medical data that we need to make all this useful.
Giannis, I think you bring up a great point. And I know our strategy had been to extract the information from the notes first, but then of course you're extracting the information that you see as important from the notes. And therein lies some limitations to that. So we tried redacting information from it, but that becomes very challenging. That could be a whole nother discussion. As you're saying, though, the information is vast in the notes. So yeah. One of the questions that came in was, in many cases when using real data, there's a cleaning step. There's a large cleaning step. Is this also required for synthetic data, and is there a validation step? I think I'll take a stab at a little bit of this, and then we can move to others, but I also think it's the purpose of the synthetic data. So for teaching purposes, we intentionally left errors in the data, or we made sure that there were errors in the data so that the students would have to clean them to understand when they were going to get the real data, this was going to be a real issue. The other use case where that came in very handy was when we were working with vendors, and it became clear to me that, say a company came and wanted the data because they had an algorithm for sepsis and they knew that this was going to be, great. But honestly, they had never even really worked with the clinical data in its raw and ugly format. So that was another reason that we intentionally left that in. But as far as using other synthetic data, I will pass that back to the other panelists here.
Yeah, so I can very quickly say, yeah, so there needs to be a cleaning step, and obviously there also needs to be a harmonization step, which is something that was also asked in an earlier question I saw. Obviously, the assumption here is that whenever you do these types of federated learning, and people are using different schemas, and they're storing different types of data or different units and things like that, there needs to be a harmonization step. Otherwise, all the other models that we learn are not going to be useful at all. So certainly cleaning all the let's say all the requirements for traditional machine learning are there. Right? So cleaning, harmonization, schema alignment, and all these things need to take place. Otherwise, you cannot have a meaningful learning task.
Maybe an interesting element is the fact that you can correct the data with correcting bias. You can have imputation of missing data. So in fact, you can turn up with certain controls by having better data sets than you had originally, because you combine the things which are missing, you clean it up, you add other things. This is especially important for rare diseases, where it's difficult to have enough data. So these are elements by which need still to be explored. But theoretically, this is a great potential of using synthetic data with differential privacy as an element of the generating algorithm.
Yeah, sure. I think imputation is definitely a good thing. Removing biases, I think, is a little trickier. That's something that needs to be thought out, and I think there's a lot of work in ethical AI and so on. Now, saying that the synthetic data set is better, I think that's a tricky statement. I mean, in a sense, the real data is what it is. It's not, if I generate something that's cleaner and I don't know, doesn't have any holes and things like that's not necessarily better. I think in a sense the golden standard is the real data. So, but on the other hand, I think the fact that even if I have a very small data set, I can generate a model, and based on that I can actually produce as many examples as I want and so on. I think that it gives you a lot of flexibility to test a lot of things. Of course, there's also the issue of how we validate. I think that was another question that was posed. How do you validate techniques on synthetic data and so on? I think there's many open issues. Like there's various strategies that people use, right? So you train on the real data set, and then you train the same model on the synthetic data set. But what do you test it with? You should test it with real data, right? And so there's many different types of there's many different types of questions that need to be answered, I think it's a very rich area for research in the years to come. But one thing that is very clear is that we need data, and things like GDPR make it hard to share data, and I think we need to find ways around it. And to me, this seems like a really viable alternative. At least, as I said, I wouldn't be using these data sets to actually do patient diagnosis, but I would use it to explore the data and try to figure out patterns and find interesting trends.
So I know we have about 4 minutes left. We have another, well, maybe we have a couple of questions. One is, as part of scientific reproducibility, is there a best practice, sorry, this keeps moving, for sharing synthetic data and accompanying analytic routines that were used in a study? I don't know about best practices. I will say that I know there's a company called CodeOcean, and I know Pierre from that. And it's been amazing to see people putting in synthetic data to allow someone to reproduce their methodology for their studies. But I don't know if there's a best practice for that. I don't know. Edwin, Yanis, Minos?
Experimentations going on, people using synthetic data for in silico clinical trials, trying to create virtual cohorts of patients when needed, and seeing things like that. So these will be best practices once they've been developed, but this is ongoing work.
Which is why it was a very salient topic to bring to RDA, I think, this year. So, and the Health Data Interest Group.
If I may, I think the synthetic data for reproducibility is more important to share the methodology by which the synthetic data were generated and the characteristics, not the synthetic data itself. Because then it will not be, it will be true reproducibility and not just repeatability. And how do you do that without sharing the actual basic data? I think it's something to look into, but I think that would be the reproducibility that will be truer to the meaning of reproducibility.
And on that, I think we have 1 more minute. Edwin, that was a great way to end it, but Edwin, it's back over to you.
No, well, I'm happy that this was brought up. I'm happy to see that this discussion, on which personally I stumbled practically, because looking for data, which I couldn't find, I agreed with some hospitals to have the synthetic data and do a number of things. And then I saw that this was a theoretically interesting issue and raising a lot of interest also at the European Commission level. And this went on, and so we discussed with colleagues, etc. Now this has become a hot topic, as shown by the literature, which is growing up right now. I think that it was important to bring this. We had already spoken about this, but more vaguely during our discussions in the Health Data Interest Group. I think it was interesting, and we must keep an eye on what will be the concrete developments of this. This is all I want to say now.
Yeah, I just want to answer to the comments that I'm saying. By no means did I mean to say that GDPR is a bad thing. Okay, GDPR is definitely a good thing, and I agree with all the points that are made in the discussion, that the homogenized sharing of data and so on. I'm just saying that after GDPR, people are more thoughtful, and as they should be, of course, about sharing data, and more cautious, right? So I think, that happens whenever you put legislation over such a sensitive topic, which you should, of course, put legislation. And I think, definitely GDPR was a big step, but now I think one thing that GDPR is I would say, as a technical person, when I read GDPR, one thing that I found difficult is trying to put privacy in concrete terms, and I think that's in a sense, that's what we're trying to do with differential privacy and all the efforts that we're doing here. And I think we're slowly making progress towards that. And I think eventually, when we make it, I think GDPR will actually be, as is said in the discussion, is going to be a vehicle that helps progress towards sharing data. And I completely agree with that.
I think our time is over. So I want to thank everybody for having attended this session. And thanks to the RDA for making it possible. Goodbye, everybody.